Okay. So can you hear me well? Yeah. So, okay. So as I was saying before, thank you, Giovanni and Max, for organizing these master classes and for inviting me. And especially thank you for all the time that you give to PLUMED and this project, which I really like being part of. My talk will be about this enhanced sampling method that I developed together with Professor Parinello during my PhD. And it's called on-the-fly probability enhanced sampling method, or OPES for short. A brief outline of the talk. First, I will give you an idea of a unified approach to enhanced sampling, to give you a little bit of perspective on what is the OPES method. Then I will tell you about how to use OPES for replica exchange like sampling or for metadynamics like sampling. And finally, we talk about exploration convergence trade-off that one has with adaptive biasing sampling. So, a unified approach to enhanced sampling. I think you're all familiar with the concept of enhanced sampling. It's helpful to study rare events with molecular dynamics simulation, and allows you to discover the metastable states of the system and calculate free energy differences. Examples of rare events are, for instance, conformational changes or phase transitions. Basically, most of the phenomena of interest for molecular simulation have this kind of sampling issue. For this reason, throughout the years, a lot of different enhanced sampling approaches have been proposed. I've taken this image from this recent review that is I find very nice, that gives you an idea of the complexity of the landscape of enhanced sampling. But here they try to categorize all the sampling methods based on how they work. So you can find adaptive bias potentials or adiabatic methods, replica methods. But I want to propose a different kind of classification that can be complementary to this one. And the idea is to look instead to how these methods sample, to look at what they sample. So to focus on the target probability distribution that is sampled by the methods once they are at convergence. If we do this, this complexity reduces to mainly two families. There are, of course, outliers like path integral method, path methods, or path sampling methods, or non-equilibrium methods. But mainly, all of the enhanced sampling methods mentioned before belong to two main families. So, which are these different kinds of target distribution? The typical situation is this one. You have your phase space with, let's say, 3 metastable states. You run your molecular dynamics simulation and you just sample one of them. Then, in some cases, for instance, it might happen that if you increase the temperature of your system, you're able to visit all of the states. Then a method like parallel tempering enhances the sampling by combining different temperatures. So this is the first kind of target distributions. I call it replica exchange-like, or expanded ensembles, or generalized ensemble. Many names can be chosen. But the idea is not just with temperature, but one can expand in this way and the sampled ensemble and obtain an ensampling. The other family of methods, you might already be guessing them. It's the other possible strategy to choose a target distribution is to identify an order parameter that distinguishes between these metastable states and use it to project along this collective variable, and you can obtain a free energy. And then in this metadynamics-like target distribution, what you do is basically you are asking for a specific target marginal distribution along this collective variable. For instance, you want that the free energy of your target distribution is flat along this collective variable, so you avoid the barriers between the states. So these two ways of defining a target distribution are the two main ways that an ensampling uses to define this target distribution. If you think about it, you can bias both of these family of target distribution. You can sample both of these target distributions by defining a bias potential that looks like this one. So, okay, this is your target distribution, and this is the original Boltzmann distribution that is hard to sample. By defining a bias potential in this way, you can sample the target distribution and then reweight to obtain any statistical of any observable along in the original Boltzmann sample. So what is the problem with this? That typically you don't have access to this target distribution is unknown, so you cannot explicitly write this bias potential. So you need a way to optimize for it. OPES is a method that provides you a way to iteratively build such bias potential. So just to sum up a little bit, if you can choose a target distribution and then add a bias potential to your system such that you're sampling this target distribution, you can reweight and obtain information about the original Boltzmann distribution that was hard to sample. OPES is one way to iteratively calculate this bias potential. The way it works is extremely simple. The idea behind it is that you want to sample this target distribution by adding the potential to the energy of your original system. Then on the fly, one sample at a time, you calculate via reweighting an estimate of the probabilities, and you use those to define the bias. So ideally, this loop will allow you to always have a better sampling of your target, a better estimate of your probabilities, than getting closer and closer to the correct bias. This is the basic idea behind the OPES method. This was a rather abstract introduction to allow you to better understand what I'm talking about. It's better to start with some examples. So first, I will tell you about using OPES for this replica exchange-like sampling. So the target distribution will be an expanded ensemble. Again, the easiest probably expanded ensemble is the one sampled by, for instance, parallel tempering. So it's an expansion in temperature. Let's say that we have a given inverse temperature beta. This will be the corresponding probability distribution, where U is the potential energy and Z is the partition function. Then we can choose a set of temperatures and define the target distribution in this way, simply by summing all of these probability distribution. So this one in purple is the target distribution defined by this temperature expansion. Just to be clear, the typical situation is that one is interested into the sampling the lowest temperature, but that is hard to sample. For instance, there is a rare event. Whereas at a higher temperature, it's easy to sample, so there are no barriers, no? Then one, in order to actively define this target distribution, one also needs to have intermediate temperatures, sometimes also many intermediate temperatures. Why? Because you want these two distributions to overlap. Otherwise, your target distribution will be hard to sample itself, will have a barrier in between. So this is why you need to combine a lot of temperatures together in order to define these expanded ensembles. But the result is that your final target distribution has a good overlap with the original low temperature distribution, which is the one you were interested into. and also a good overlap with the high temperature, that is the one that allows you to go through these metastable states without getting stuck. So I hope this makes it a little bit more clear. So how do you write explicitly this bias potential for targeting these expanded ensembles? So first of all, let's choose a temperature. So this will be our reference. We will run a simulation with this temperature. And then we can rewrite all the other probability distributions at different temperatures as a function of this temperature here. And I won't go into the details. I put all the equations here so that you can check afterwards if you're interested. What I care about telling you is that basically you can rewrite your target distribution as your P of X times something. And this means that when you have to write the bias potential, these two terms cancel out. And your bias potential does not depend on the Boltzmann probability distribution anymore. And this is good because this is a very high dimensional object and it's also hard to sample. So the fact that it cancels out is very important. And also we can see that the bias potential is actually just a function of the, depends on the coordinates of the system only through the potential energy. So as a matter of fact, we can look at the potential energy as a collective variable itself, and the bias is no longer a high dimensional function, but just a function of this collective variable. But again, this bias is still an unknown because we don't know the ratio between these partition functions. We can rewrite it as a free energy. And the idea of OPES is use reweighting to estimate these free energy terms. Of course, if you try to estimate these on one single temperature, there is basically zero overlap, so it's very hard to estimate these things. Instead, if you are trying to estimate those by sampling the target distribution, it becomes easy. And this allows the iterative procedure to work. So just to explicitly write all the equations, but again, I don't want you, I don't mind about the details now. Just to show you, these are the two key equations. One that defines the bias at step n, which is a function of this estimate that is obtained through reweighting. And this is the OPES scheme in action. You can of course rewrite this in a more general way and define any expanded ensemble target as a linear combination. By the way, you could put some weights here. In this case, all of them have a uniform weight. But the basic idea is this: you have your target, and just by choosing this target, you obtain an expression for the bias that you can feed to OPES in order to sample this target distribution. No extra things required, no other input parameters required. Basically, these quantities here that we call expansion collective variables are the ones that define the target, and that's all of the procedure. But anyway, let's put an example on the table. This is alanine dipeptide molecule. Probably many of you are familiar with it. And we can run a multithermal ensemble. So sampling from 300 to 1000 using OPES. You can do this with parallel tempering. You would have to use 3 replicas. With OPES, you can do it with only 1. And again, the only input that you need to give to OPES is what's the temperature range that you want to sample and how often you want to update your bias. As you can see, these are the weights of the reweighting for 300K, and these are the samples from the target distribution. What happens is that the probability of sampling one of these transition states is basically 0 in the 300 Kelvin ensemble. And this is why it's a rare event. But in the higher temperatures, these are more likely to be sampled. And so in the final target distribution, you get samples also from the transition states between the two samples. Another interesting expanded ensemble is what I call multi-umbrella ensemble. And you obtain it by combining the original Boltzmann distribution with some Gaussian at a different placed at a given collective variable position. So you have to define a collective variable in this case, and these Gaussians means that you are adding a bias potential that has a parabolic shape in this collective variable space. Just to be more clear, this is what is sampled by multiple windows umbrella sampling. But in that case, what you do is that you have many different replicas of the system, and each one samples one of these probability distribution that will be combined to form the target distribution. And you estimate the free energy difference between these in post-processing. Whereas if you do this with replica exchange or with OPES, you do it on the fly during your simulation. So this is just to say, multi-umbrella ensemble is another kind of expanded ensemble that you might be interested in sampling. This is so this ensemble allows you to sample along a collective variable. But it's interesting to notice that you are not deciding the marginal over this collective variable. In fact, once you choose a number of umbrella windows, you don't know what you're going to sample. What you know is that in the limit of having a lot of narrow umbrellas, all of them overlapping, and this is what I'm showing here in this GIF, that as we increase the number of umbrellas, we will sample a flat marginal probability distribution along the collective variable. But usually you stop at a much smaller value of, at a much smaller number of umbrellas, and you sample something that is in between. What you care about is just that the probability of going from one basin to the other is non-zero. So this is just to say you can sample along a collective variable with expanded ensembles. It's just a slightly different way of doing it. Okay, why is this interesting? Well, it's particularly helpful to sample combined expansions. So, for instance, in this example, we want to study the phase diagram of sodium that has a solid-liquid phase transition. So we are going to run an expansion in temperature and in pressure, plus biasing crystallization collective variable to allow for the phase transition to happen. This is very important because if we just look at one of these points in the phase diagram and we plot the free energy along this collective variable, we can see that, for instance, at high temperature, you will likely see the liquid configuration. At low temperature, you will likely see the solid configuration, but there is no combination of pressure and temperature where you are likely to see a mixed phase. So this means that if I only use a multithermal multivariate target distribution, that will not be an easy to sample target distribution. So I need to also add this collective variable in order to sample this. The effect of running such OPES simulation is that without the OPES bias, you would sample just one temperature and one pressure. And these are the samples in the volume energy space that you would get. Instead, by adding this bias, you sample the target distribution, which covers a much broader volume and energy range, and you can reweight for any point in this phase diagram at any pressure and temperature. Of course, you can do this also with replica exchange. The main difficulty is that for this specific target distribution, you would need more than 800 parallel replicas. because because of the many expansion collective variables that you're using. With OPES, you can use any number of parameters. Okay, so let's move to metadynamics like sampling, which was actually the first application for the OPES. I will go a little bit faster because time is flying. So again, here we want to instead use as a target, define the target through the marginal distribution along a collective variable. A collective variable, I'm sure all of you know by now, it's a function of the full coordination space. You can use it to define the marginal probability or the free energy surface in this way. So here we have a two-state system, for instance, liquid solid again, and these are the probability. What you want is to be able to freely go from one state to the other and to avoid the rare event in your simulation. So you have to increase the probability of seeing the transition state. A natural way to do this is to add a bias potential that was proposed already in the 70s by this umbrella sampling semi-hypothesis. So one way to do this is if we choose a bias potential along this collective variable that is equal to minus the free energy, we will have a target distribution that is completely flat along the collective variable. Another way that is used mainly with metadynamics is to define instead a well-tempered distribution that you just add this factor here, and your target distribution still has what you want. So the probability of crossing between the two states is much higher. And this is the definition of the well-tempered target distribution. So once you are able to sample this target distribution, then again, you can sample any given observable ensemble average, for instance, in the Boltzmann ensemble by reweighting. So the target distribution, it's chosen by setting its marginal distribution along the collective variable and requiring that the bias potential is only a function of this collective variable. If you think about it, if I just ask the target distribution to be flat along not only this collective variable, but all the degrees of freedom of the configuration space, then I would have no energy barriers, but my target distribution would be useless because the efficiency of the reweighting would be zero, because I would never sample relevant configuration. By choosing instead one or few collective variable, I can do this in a much more efficient way. So again, the free energy, it's unknown, and so also the bias. One way to get to this is to use metadynamics, which is an iterative procedure to build this bias in such a way, by depositing Gaussians, in such a way that in the limit, I obtain the bias potential that I need to sample this target distribution. This also gives me two ways to estimate the free energy. One is a direct estimate, which is by inverting this formula. And the other way is to do reweighting, as we said before. But since the metadynamics bias is always changing, doing reweighting in metadynamics is non-trivial. There have been several different possibilities of doing this. Anyway, metadynamics is a great method. It's very rigorous, but can also be quite inefficient, especially if you are using suboptimal collective variables. And here I will open a parenthesis because I want to tell you about this suboptimal collective variable, which is what motivated me to go beyond metadynamics and look for a different way to reach this target distribution. So a suboptimal collective variable means that you are missing some slow mode of the system, some slow degree of freedom of the system. The easiest way to picture this is by thinking about a two-dimensional system in which your non-collective variable would be the x-axis and the unknown slow degree of freedom is the y-axis. If you run metadynamics on this, what you will see is that the free energy estimate, so the bias that the metadynamics is using, keeps on oscillating. And the idea is that you are overshooting, so you are adding much more bias in order to accelerate the transitions. And you're sampling a very high free energy regions here that are not in the real transition state of your system. You can see this clearly from if you plot the time evolution of your collective variable. You will see hysteresis, so you can see that you have this kind of behavior. So the place where you make the transition keeps on changing as you go along. By the way, I should have said this is well-tempered metadynamics, so eventually the bias becomes constant. And you can see at the very beginning, the bias changes a lot and you have these very fast transitions. But these are the bad ones, no? Because the truth is that in order to have a transition, you need to wait for this slow degree of freedom that you're not biasing. So you are forcing the system into this higher transition rate, but by doing so, you're not actually seeing the system, but you're just seeing the bias. And if you plot the estimate of the free energy difference between the two basins, you will see something like this. So you have an oscillatory behavior. The question is, can we do better? No? Can we teach metadynamics without knowing beforehand? Because of course I can change the parameters of metadynamics and tell her to be more gentle. But if I don't know the system beforehand, can I avoid these oscillations of the estimate? The answer is yes. The OPES method does this in a much nicer way. And you have these very damped oscillations and a better estimate of the free energy on average. If you look at the collective variable, again, as a function of time, for OPES, you don't see this hysteresis. And what you see is instead much fewer transitions. Because, again, if you have a static bias or a quasi-static bias, this is the time you have to wait for a transition to happen. So in this case, we have fewer transitions, but this gives us a better estimate of the free energy. So in the detail, how does OPES work when you want to use a target bias, a target marginal distribution? The idea is, again, you sample your target probability, you reweight. This time you directly reweight the P of S. So you basically, this is your free energy along the S coordinate by using a kernel density estimation. And from this estimate of the probability, you update your bias and you use it for sampling and so on and so forth. Basically, it's the same idea underlying the same idea has been around for a while. This paper, adaptive umbrella sampling, proposed the same idea, but we added some key new elements that allow us to overcome important limitation of similar methods. I will go quickly through these elements, but again, you will have the slides, so you can have a look at them afterwards. The first two things are taken directly from metadynamics. So we have the probability estimate that is updated on the fly, one sample at a time. And we have seen with metadynamics that this allows for a faster convergence. And again, we don't use a uniform distribution, but a well-tempered. The other new elements are, we added a a regularization term. So basically, we don't want to, usually one has an idea, a rough idea of what's the barrier of the free energy barrier that one wants to overcome. And we can tell the OPES simulation not to go beyond that. And this allows us to avoid extremely high free energy and physical states. Metadynamics, if you've used it, tends to always overcome any barrier, no? So also barriers that you don't want to overcome. So this is a very built-in feature that allows to avoid that. Then we use this adaptive bandwidth kernel density estimation with a kernel merging algorithm. Again, I won't go in the details, but the idea is that this gives a nice a nice way to estimate the probability, and especially a way with very few and robust parameters. You can visualize this. This is again alanine dipeptide. Basically, when we need to add a new kernel to our estimate, if there's already another kernel close to the place, we instead merge the two kernels. So instead of having to build, for instance, a grid or something, this only places a kernel where the simulation in the regions that have been visited. So it's extremely efficient, and the number of kernels needed for the representation of the probability and thus of the bias does not linearly increase with time, but remains small. And this also allows to go from a cursor to a final description, because you start with bigger kernels and then they shrink over time. Finally, another important innovation, I would say, is to add a normalization term over the explored space. This is a tricky concept. So one of the problems of this kind of adaptive umbrella sampling schemes is that you want your bias to become quasi-static as soon as possible, no? But then what happens is that the rate at which you let the bias change diminishes very fast. So you're quickly to adapt to the first basin that you encounter, but once you find a new basin, it takes you a very long time to escape from that one. What we did basically was to teach the system that allow the system to understand that it's visiting a new region of the collective variable space. And if it finds itself in a new region, then it will adapt quicker. And so we avoid this second exit time problem that has been described in the literature. This turned out to be especially helpful for higher dimensional systems, because in a higher dimension, the volume grows much faster. So you really need this kind of term in order to be efficient if you go to 2, 3, or more dimensions. The details of how this is calculated, are not. I won't go through them now. But it's nice because it makes use of this compression representation of the probability distribution. So to summarize, these are the two key, again, as before, the two key equations of OPES, but this time in case of, for sampling a collective variable. The bias potential, that is a function of this estimate of the unbiased probability distribution, which is built by a railway. Here I put the original version for the bias in adaptive umbrella sampling. You can see that there are quite some differences. Plus, these are the other terms to be completed. So this is a Gaussian and so on. But again, I won't go into this detail. You can find all the details in the paper. What I want to do instead is to give you an idea, to visualize the difference between, again, OPES and metadynamics. This time with the alanine dipeptide example in 2 dimensions. So these are optimal CVs, but still you can see that the metadynamics estimate kind of oscillates around the true value, while the OPES one has very much more damped oscillations. And you can see this also in the 2 dimension. This is just the free energy difference between the minima, but you can also see it from the 2-dimensional estimates. If we look at the very beginning of the simulation, this is just the first 10 Gaussians. Metadynamics only explores a very small region of the CV space, while OPES starts to place very big kernels again. It starts from a very coarse representation, and already at 100 Gaussian, already has the main features of the final free energy, and also the value of the free energy difference between the 2 bases, which is the hard quantity that one needs to calculate. It's already kind of in the range and won't change much throughout the rest of the simulation. Then when we go ahead, OPES just focuses on fixing the details, whereas metadynamics, again, has this kind of oscillatory behavior more. Now, one thing that we realized is that quickly converging is not always the best thing to do. And in fact, there is a trade-off between your exploration speed and your convergence speed. And this trade-off is due to, again, suboptimal collective variables. I'll explain this with an example. In this paper, we were studying a perovskite system, a change of phase in a perovskite. And we did this with metadynamics and a collective variable, again, that measures the crystallization, how far you are from a given crystal structure. What we found is this kind of behavior. This is the collective variable as a function of time. And it was nice because we were able to identify 2 intermediate phases that were not known before, and that had been observed then afterwards in an experiment by some experimental group. So the goal of this was not to calculate free energy differences. As you can see, we don't even go back to the original, to the initial state, not even once, but was more to discover new metastable states. The reason is that this collective variable was extremely degenerate. So if you look, for instance, at this value here, we have a transition state between these 2 intermediates. Here we have something that looks like a metastable, another metastable state. And so this means that if we just use a static bias, basically we would get stuck. So we would not be able to exit these metastable states because the collective variable is not good enough at distinguishing them. But instead, it turns out by using this quickly changing bias, we were able to actually observe this and discover these metastable states. So when you have a degenerate or a highly suboptimal collective variable, it might be practically impossible to converge if you use a static or quasi-static bias. But instead, as we saw, sometimes if you allow your bias to adapt and change, even after the initial phase of this the simulation, even if you've already been here, but you go there again, you allow the bias to change again, you might be able to escape and explore faster this space. This can be helpful, for instance, because finding all the metastable states can help you to then improve your collective variable and understand what was wrong with it. So again, the point is not always trying to converge as fast as possible is the best strategy. So what we did was to develop a variant of OPES that's called OPES-explore that is more similar to metadynamics. So it focuses more on fast exploration rather than on fast convergence. the nice thing about it is that the implementation of this OPES-explore is basically identical to OPES, except for one key modification. So this was the scheme for OPES. This is the bias potential that you have to use. You then do reweighting and estimate your unbiased probability and go again in this loop. So basically you use this, the relation between your unbiased probability and your target well-tempered probability to write everything, all the bias as a function of this unbiased estimate. In OPES-explore instead, what you do is you estimate the sample distribution. So now this is a kind of kernel density, but the weights are all equal to 1. And again, you just invert this relation and you can write the bias as a function of the sample target distribution. With this simple change, you obtain a very different behavior, because now, now you are looking at you base your bias on the on what you're sampling, and so basically the methods will tend to sample the target distribution rather than tend to converge the probability distribution to the unbiased probability distribution to a static one. So from a practical point of view, if you compare this OPES-explore method to OPES, what you will have is a faster exploration, especially with suboptimal collective variable, but at the cost of a slower convergence, because if you let your bias adapt, it means that it's not converged, it's not a quasi-static bias. A nice thing is that it requires fewer kernels, because it's estimating, again, this broader probability distribution. So the kernels will be broader, and you will need fewer kernels to do this estimation, which can be good for when you are working with higher dimensions. But again, this comes at the cost of a more noisy bias estimate. If we compare instead OPES-explore with metadynamics, we still have the straightforward reweighting of OPES. We still have the controlled exploration by setting this barrier term and have a limited maximum bias, so the bias won't grow indefinitely. And we have fewer input parameters, because basically we just need to decide what's this. We just need to tell the system what's the barrier that we want to overcome. So this makes it a very nice method for quickly testing new collective variables. For instance, when you use machine learning collective variables, often you cannot rely much on the physical intuition to choose the input parameters of metadynamics. So it's good to have this kind of method. And as a matter of fact, it has been already used, this OPES-explore method, to study, to explore chemical reactions with machine learning collective variables. So with this, I've come to the conclusion of my talk. I've presented the on-the-fly probability enhancement method, which provides a general approach and can be used for various enhanced sampling strategies. The method was built with in mind with the goal of being simple to use, with few and easy to choose parameters, and to be efficient and robust, especially with respect to suboptimal collective variables. I've presented you 3 variants, which are all implemented in PLUMED, and are this OPES expanded OPES method and OPES method explorer. It's available in PLUMED as a contributed module, and on the PLUMED Nest you can find a lot of examples of papers that used OPES, and all the input files are available there. With this, I've reached the end of my talk. If you have questions, I would be happy to answer them. Okay. So if there are no questions.
May I ask something?
Yeah, sure.
Thank you for the great talk. I really would like to try this method, but maybe it's a stupid question, but may I ask in practice which parameters we have to choose when we use OPES?
Yes, sure. With this,
probably you already said it, but maybe.
So it depends. It depends on again. Basically, you need to define your target distribution. So if you are sampling, if what you want to sample is, for instance, this kind of ensemble, a temperature expanded ensemble. So you want to run a multithermal simulation, then you need to decide which are the temperatures that are going to be in your target distribution. If you want to sample instead in a metadynamics like simulation, you will have to choose basically you will have to choose what are the barriers in this in this free energy surface that you want to overcome. So you might be interested into overcoming a barrier of 100 kJ/mole or just 30, no? So depending on that, for instance, in this alanine dipeptide example, we are not sampling anything in this region. Why? Because this region has a free energy barrier that is higher than what we said in the input. Instead, we are able to sample the region, the transition state in between these two states. But the best way to see what kind of parameters go inside is to go through the tutorial that I prepared, where there are various examples. Again, there's going to be alanine dipeptide, and I provided also input files to run very short OPES simulations and to start getting a sense what it means to choose the target distribution and or what kind of parameters you need to sample. So in the example of biasing two collective variables, which are again the simulation I've shown before of alanine dipeptide, this is the input that you need. So you need to provide the collective variables and then tell the OPES method which are the collective variables, how often to update the bias, and what's the barrier that you need to that you want to overcome. If here instead of 40, I would have put I don't know how much is that barrier, probably something like 90. Then I would have sampled all of the. Let me get rid of this. Then I would have sampled also this region here. So it's really a few parameters. But then you can, if you want, you can also tweak and change a lot of internal parameters that are just, they're supposed to have a reasonable default, but you can, they should be robust, but then you can also change them if you want. Yeah.
Okay, so the barrier is almost all that you need, the collective variable and the barrier.
Yes.
Okay, very good. Thank you.
And this, for instance, allows you to, if you now want to sample not alanine dipeptide, but I don't know, its bigger brother, which is alanine tetrapeptide. So it's it's the same system, but instead of having one phi angle, it has 3 phi angles. But all of the physics is similar. So also the barrier in between them, it's the same. You expect it to be the same. Then this is the input that you need to sample that system with maybe 3 or 6 torsional angles. You just need to add the torsional angles to the argument, and that's it. You don't have to define a high dimensional grid or something. I don't know if you have used metadynamics before. I'm giving for granted that people are familiar with maybe too many things. So here, especially metadynamics, but also maybe umbrella sampling, replica exchange. There are very nice masterclasses from last year that go through all of these arguments if you need a refresh. So, of course, if there are other questions, just tell me. Otherwise, I'll go through very quickly through the, since it's already 5, through the tutorial. So here there is the usual web page on the PLUMED manual. It's just an overview of the tutorial. All the instructions are actually in 2 notebooks that you can find at this Git repository. So you can go through and just quickly read this page, and we'll give you an idea of what you're gonna do. And then all the details are in the Jupyter notebooks. I think it should be pretty clear. I will be available, of course, on Slack if you have any questions, or if you're curious about something, if you try to run something and it didn't work. But the main idea of the tutorial is just to give you some examples and to let you play around with them. So change some parameters, do some things, and I provide a bunch of scripts to do the post-processing and plot things that I think are useful to plot and to understand better.
Could I ask one quick question about the presentation? I think I understood you to be saying you have some approach for combining different clusters. Does that mean, so when you have these distributions that you're setting up, you're essentially weighting each ensemble to get one combined ensemble? When you're doing this clustering, are you changing the set of ensembles that you're combining? So you're like reducing or adding?
So you mean this example
here?
Yeah,
the kernel merging.
The kernel merging, sorry. So this algorithm is actually very straightforward. So usually in kernel density estimation, you have a sample and you place a Gaussian on top of that sample. Mm-hmm. And then your density estimation is the sum of all of these Gaussians that you placed in where you sampled your distribution. Mm-hmm. This kernel merging algorithm, what it does is that if you already have a point that's close to where you're going to put the next, so I sampled the next point, I'm going to add a kernel. If I'm within a range that in this case, the default is just 1 sigma, mm-hmm. Instead of adding a new point, you merge the two. And the merged kernel will have a height that is going to be the sum of the heights of the kernel. And the position, it's the weighted average of the positions of the two kernels, weighted on the height of the kernels. And there's a similar equation also for finding out what's the new covariance of the kernel, or the new sigma of the kernel. So it's very straightforward. And in fact, it doesn't work great. So it was developed it was some machine learning paper. And the idea was to, again, reduce the number. The problem with kernel density is that it scales linearly with the number of samples. So it can become very slow. And this is a very rough approximation. But used in this context, since we are biasing with the bias that is built on these kernels, basically there is a self-healing loop. So if I place a kernel and I move it too much and I leave an empty space, then I will sample again that point.
Right.
So there is this nice, so in the original paper, they said, okay, we have this very easy way to combine the kernels. It's not great, but we can live with that. When I applied it to biasing simulation, it turned out that it was super effective because it was able to auto-adjust to the thing. So yeah, it's a very simple algorithm. The details are in the supporting information of the paper. I've put all the references.
Yep, I'll take a look at that. And just to make sure I'm clear, the actual biasing potential you use in this example has sort of one term for each kernel, essentially. Is that correct?
Okay. Where is just this is enough. So the kernels are these Gaussians.
Yep.
And they sum up to the estimate of the probability. And then the bias depends on the estimate of the probability. So in metadynamics, you would have that the sum of the Gaussian it's the bias.
Yep. So you have an estimate at each kernel and you are using each kernel, basically.
Yes, but only the compressed kernels.
Right.
So otherwise this would grow linearly with simulation time, which becomes extremely inefficient. Metadynamics, in order to avoid to have to sum over all of these kernels, what they do is they store the value of the sum on a grid, which works great for 1 dimension and 2 dimensions. 3 dimensions starts to get problematic.
Yep.
And it's problematic also if you don't know beforehand the range of your collective variable.
Yep, I think I understand. That's really cool.
Okay, thanks.
Thank you.
Okay, then I think that, I mean, this is it. You can have a look. I think the best way to learn the method. There are, like, in my opinion, there are 2 levels. One is let's try to use it, and then if you think that it works for you, if you see something that's interesting, then it's worth to go through all of these equations and so on. I think they're very interesting per se, but I understand that they become more interesting once you start using the method. So I think the best way is to try to do the tutorial, and then if you have questions, I'm always available. And yeah, that's it. Thank you for your patience, and see you on the Slack channel. Bye.